Well, welcome to our seminar today. And I'm Luigi Burzio. It's my pleasure to be introducing our speaker today, Dr. Vito Pirrelli from the Institute of Computational Linguistics in Pisa. Vito received a degree from the University of Pisa and a PhD in computational linguistics from Salford University in the UK, with a dissertation titled Morphology, Analogy, and Machine Translation. He is currently research director at the Italian National Research Council, Institute for Computational Linguistics in Pisa, and also teaches at the Department of Linguistics at the University of Pavia. He is the author of 2 books and several, too many to count, journal and conference articles in computation and theoretical linguistics, and has worked in several different areas that include machine language learning, computer models of the mental lexicon, psychocomputational models of morphology learning and processing, hybrid models of language processing, information extraction, and theoretical morphology. In particular, in recent years, he has been doing very interesting work in morphology at a time when it's become increasingly clear that the study of morphology requires computational tools. We find in particular that frequency is important in determining whether morphology can be regular or irregular. We find that size of morphological classes determines, again, whether regularity or irregularity is found, whether or not phonology can interact with morphology. We find that individual morphological forms can be controlled by whole sets or gangs of different morphological cells in morphological paradigms, and that calculation of overall similarity of forms is also very critical to understand how morphology works. Vito is working very effectively in this context. He is making an impressive effort in bringing together observations from linguistics, psycholinguistics, and psychology to define a range of problems to which computation can lend the appropriate tools. The title of his talk today, in which he will tell us about some of this work, is Axioms, Asynchronous, Cascaded, Self-Organizing Maps for Language Learning. Vito Pirrelli.
Thank you very much. First of all, let me say that I'm delighted and honored to be here, and I'm very grateful to all the people like Luigi Burzio, Fred Jelinek, that have contributed to making this possible. It's a great privilege for me to present some pieces of the work that kept me busy over the last 2 years, maybe longer than that, to so many outstanding scholars, you know, that have represented for me over the last years constant sources of knowledge and inspiration. So I'm looking forward to getting their feedback on these fragments of work and in giving me their assistance in my attempt to put together these stray pieces in a kind of more coherent picture and vision. So one of the basic goals I set myself to when I started preparing this talk was to try to provide you with a kind of outline description of the basic principles of functioning of a particular family of computational networks, which we developed, a kind of original model which we somewhat pompously dubbed axioms, synchronous, cascaded, self-organizing maps, which are unsurprisingly based on self-organizing maps technology, which was developed in Finland over the 80s, basically, and which we used as a way to simulate some non-trivial interaction between short-term and long-term memory processes going on in language learning in general, and in particular in the unsupervised acquisition of morphological knowledge, more specifically. So by observing the behavior of this particular family of networks, we believe we can gain some non-trivial insights into some processes governing the architecture of grammar, and in particular some principles governing the organization of morphological knowledge in what we may call our mental lexicon. So these are the basic aims and the basic topics I would like to touch upon over this talk. And this is a kind of short overview of the talk. Another line of thought I would like to pursue with your help is the possible, interesting, I think, and I hope you will agree with me on that at the end of this talk, interesting connection between this line of work and another piece of work which is connected with psycholinguistic models of serial recall, which is a kind of literature I've been finding over and over more interesting and more fascinating. So I will dare to claim, in spite of some claims to the contrary, and this is one example of claims of this kind, that psychological models of memory, in fact, are not too simplistic and crude to account for even the simplest linguistic facts. As John Goldsmith pointed out to me in a kind of personal communication, I believe to the contrary, that we can gain a lot of insights by inspecting, by going through this kind of literature, because they provide a kind of new view, new, at least from my point of view, as a computational linguist, and if you like, as a cognitivist, cognitive science, a kind of instrumental focus on what I may call low-level processing issues, some sort of basic analysis of the mechanisms observing order and time in cognition, which may ultimately, I believe, contribute to a better understanding of the physiology of grammar. So there is a kind of grand scenario behind this interest. And I obviously will show just a fragment of this scenario, which hopefully will concoct in the near future a kind of more coherent and comprehensive picture. So in order to get kind of easy and smooth access to this type of literature, I will recap some classical typology of the typical human errors, the errors that human made in serial recall, because I want to make a connection between the kind of models I'm going to present and the psychological literature on serial recall. And in order to make this kind of connection, more transparent to linguists, here you have on the left-hand side a kind of typical errors which are reported in the empirical literature, and then some sort of correspondence, straightforward mapping onto typical linguistic phenomena, maybe most of you should be more familiar with. So the kind of typical errors which are made in serial recall, what is the task of immediate serial recall? Basically, when you're asked to repeat a series, a list of symbolic units of some kind, most of the times they are meaningless units like digits, for example. So you're asked to repeat a particular sequence of digits you've been exposed to shortly before. And this is the task of serial recall. Obviously, this list may vary in length, in complexity, even in the time and rhythm at which these particular symbols are presented to you. And you have to repeat them, you have to try to recall them. And obviously, in some cases, especially if the list is long enough, you make mistakes. And these are the typical mistakes that you, as a human subject, would tend to make. Errors as transpositions, for example, the places of two symbolic units are exchanged, and these often happen, most of the times happens when the two symbols are in adjacent position. They are next to each other. This is the most common pattern of error, but this is not the only one. Of course, you have, for example, when you say trap, you want to say tab, or the other way around. And this shows that these two elements must be co-activated at some time, and this may have a bearing on co-articulation effects in the end, if you look at them from a linguistic kind of perspective. But you have other type of transpositions, which are more long-range transpositions between elements which are not in adjacent position. They are not next to each other, but they can exchange position if they are sufficiently similar to each other. Right? So in this case, confusability in the order is determined not by the adjacency of the two elements, but just by their inherent similarity. You can think, for example, of two segments which share a certain amount of features, either articulatory or acoustic features, and they get swapped in their position. This is not the typical kind of error. For example, when you say trap for brat, right? So this introduces an issue of phonological confusability that should strike you as a kind of fairly linguistically motivated and well recognized. Another typical effect is what is called in the psycholinguistic literature, for example, by Hutchinson, the bathtub effects, or in the psychological literature as the primacy and recency effects. If you think of a list, some elements of this list are recalled better than others. There is a kind of recall advantage in recalling the first element of the list, those which actually, with which the list begins. And there is also another related recall advantage for the last one or two items in the list, although this advantage has a far lesser extent than the first one, the primacy recall advantage. So it's easier for you to recall the first elements of the string. It's fairly easy, although to a lesser extent, to recall the last units or the last symbols making up your symbolic structure. So we have, or you have, some uncertainty for what concerns those symbols which are placed in the middle, half between the start of the sequence and the end of the sequence. And this is a common phenomenon, for example, in lexical access, which was dubbed in the 80s by John Hutchinson the bathtub effect. So you remember the beginning of the word, you remember the end of the word, but you are not in a position to reconstruct the whole word because there are some bits missing just in the middle of it. And then you have grouping. These are two fascinating phenomena. We'll get through the list to give you kind of a broader picture of the situation and where we are getting at. You have two phenomena which are, yes?
Sorry, I'm trying to understand
the bathtub.
The bathtub effect.
Yeah.
I know about primacy and recency effects in, say, a series of numbers
Right.
And so forth. I hadn't heard about this for words before. Are these nonce words?
Right. You mean the bathtub effects?
Well, you said you remember the beginning and the end of the word, but not the middle. Are
Yes.
you saying for nonce words?
No. Just even for ordinary words, it's kind of lip of the tongue effects. Like when you try to recall a word which is actually stored in your lexicon, but you manage to.
You're just talking about lexical access problems.
Okay.
Yeah, okay. Tip of the tongue phenomenon.
Tip of the tongue. Sorry.
Okay. Thank you.
Okay. Right. Grouping. We were talking about grouping and chunking are two related phenomena, because grouping means that we manage to effectively retrieve some elements if they, instead of being evenly spaced in time, they are grouped according to some sort of recurrent rhythmic patterns. So items which are placed within a certain group are recalled more easily than items or symbolic units that stride the border between two groups. And there is another related phenomenon to that, which is called structural confusability. And the issue is that, two items which are far distant from each other are likely to be exchanged in their position if they appear to take the same relative position within two different groups. And this is a well-known phenomenon in linguistics, like when you say barn door instead of darn ball, even a more complicated, more complex level of word structure when you say it pays to wait instead of it waits to pay. And this obviously, this particular kind of phenomenon points in the direction of an overarching principle of language, a kind of hallmark of language, which is hierarchical organization and grouping of language. Chunking is a similar phenomenon. The notion of chunking dates back to early and pioneering work by George Miller in the 50s, the famous, the magical number 7 kind of paper. And chunking refers to the fact that obviously some particular sequences of symbols are recalled easily if they derive from some sort of background knowledge which is available to the human subject, in the sense that some sequences are stored in our long-term memory and they have an input and they have an effect on easy recollection of these patterns. So there is a kind of effect of interaction between short-term memory and long-term memory, because patterns that are already stored in our long-term memory are then eventually recognized and recalled easily, even at the level of long-term memory. So we have a kind of grouping effect here. The only thing is that the main difference between grouping and chunking is that grouping concerns short-term memory effects only and processes only, while chunking is about the interaction between short-term and long-term processes. So these are basically the classical typology of errors which are connected with serial order. Well, there is a whole family. I propose here the kind of classification that is suggested by Hansen in a series of papers in the 90s, a whole family, the different families of both mathematical and computational models that have tried to address all the various areas or classes of areas which we've been concerned with in the previous slide. Well, probably the pioneering system and the most favorite system, or if you like, paradigm of explanation in the 50s was the kind of associative or chaining model, right, which was very popular in the early 50s, but that was kind of rekindled through connectionist models of some kind, at least according to some scholars. And here, basically, the intuition is that in order to recall one particular item in the list, you have to be able to know what is before that particular item. So the way you reconstruct a list, the way you manage to recall the list is through inter-item association. This kind of chaining models obviously are obviously connected in an indirect way to Markovian models of some order. For example, if you recall one particular item on the basis of the information you have, or the item before that, that is a kind of first-order Markov model. But you have some sort of compound chaining phenomena where the order is higher than 1, and you say that in order to guess what is next, you have to get some knowledge about an entire sequence of items preceding the item in that position. So this is basically what I have to say. Well, there are some complicated issues, but this is what I have to say about chaining, and probably I will return to this particular topic in connection to some recent connectionist architecture that was recently proposed by Botvinnik and Plaut to address some problems which are connected with short-term and long-term memory effects. Well, another classical explanation, which seems in line with classical, Turing machines, is represented by so-called positional models. Positional models say that in order to recall a string, you have to make an association not between items in the string, but between kind of positional boxes or positional placeholder on the one hand, and their content on the other hand. So there is an association between some sort of placeholders that can have also a kind of, they don't have to be symbolic in a sense, they can also be activated through distributed patterns of activation. So they can have a kind of distributed representation. The basic point here is that you make a connection, a sort of implication between boxes, which a sort of a time-stamped container or placeholder on the one hand, and their possible content, which are the items that take that particular position on the other hand. And finally, you have ordinal models. Ordinal models are based on pattern of activations. Actually, they do not require a particular structure or a particular order structure in the form of a chain of containers, as it were, because they are based, if you allow me, on a kind of completely different anthropological model, an anthropological culture. You don't have like a line at a bus in London, but you have, in this case, in activation, in positional ordinal models, a situation like you find in an Italian crowded bar, where you have customers that are crowding before a single bartender, which tries, obviously, to serve one client at a time, because there is only one, but there is no fixed structure. There is a crowd of customers yelling and trying to attract attention of the bartender. So the order of service is based on success in the competition to attract the attention of the bartender, right? It's a completely, anthropologically and culturally speaking, is a completely different model, but there are obviously some connections between the two models. But I will not harp on to that because of time constraints, basically. There are some problems that some of these models can address and some others cannot. And one of the most famous problems, which I mentioned because it's interesting also for some linguistic implication, is the problem of two. How we represent in a model like the chaining models, the fact that you may have the same type which is repeatedly instantiated in a sequence, the same time which has several tokens in the same sequence, because if you guess what is next on the basis of the prompt or the cue which is given by a preceding item. If an item is potentially followed by two different, through associative links by two different other tokens, then you have no mechanism for choosing between the two associatively linked alternatives. And so in order, as I illustrate in this diagram, E can be followed by V or can be followed by I. You have no mechanism for making a choice between these two alternatives. So in order to avoid this issue, well, the chaining models adopt the kind of Wickelgren solution, so-called Wickelfunds, in the more recent kind of connectionist revival of this thing, where actually the same type is encoded into different ways because you have a conjunctive representation of the type plus its token. And this is done to solve it, to address the particular issue of the inconsistency between the chaining, but is done at the cost of treating two types as two completely and potentially unrelated tokens.
But can't you still have repeated blocks down in the bottom case too?
This one.
Yes.
This one. Well, it's the Wickelgren solution to the problem of having different types, and to distinguish between different instantiation of different types in context. So instead of having, the E, which is linked twice, once to V and once to I, you have a representation of V here, which is a combination of the particular type plus its immediate context. So it's uniquely determined.
Right. That this doesn't fully solve the problem, because EVE is sometimes followed by VEN.
Yeah. Okay, yes, I know there are, there are potentially, right. Yeah, there are obvious limitations to this kind of solution. This was just to suggest that a possible way of getting around that stuff. Right. Okay. Let me go to, well, another related issue to the same problem is that if you have just a single family of types and you try to establish different orderings by different connections between types, you have the kind of crosstalk, you have kind of ambiguity in encoding, supposing that you have a lexicon or a repository of different strings that enforce different orderings between this family of elements, then you have to have ways of avoiding this kind of crosstalk of kind of a combinatorial explosion of ambiguity in the encoding of these various words, because in our dictionary, various words can be combined on the basis of the same basic inventory of the characters. So you have cat, but you have also act, which are made up of the same set of characters. And in order to avoid that, especially in so-called ordinal models, you have a further level, a higher level of coordination of propagation of patterns of activation in a way that this is made unambiguous. But obviously, this type of representation does not avoid the problem of repeating the same item in the same sequence, as shortly shown here in the bottom right corner of the slide. Well, this problem of type, in a sense, makes a connection with this problem of type, which is usually solved of instantiations of the same type in the string, is usually connected with another problem that has been identified, for example, by work by Gary Marcus and then recently discussed extensively by Ray Jackendoff. The problem of default statements, the problem of typed variables, which apparently play a crucial role in language. So the problem of how you can express some sort of universally quantified variables that play an important role, for example, in kind of statement of default rules, like, for example, the past tense, the regular past tense in English is formed by adding a sort of ed, ending to an x, where x stands for any type of stem. Or even more critical, to this issue the fact that reduplication phenomena are rather ubiquitous in language. You have repeated elements that, no matter what they are, they must repeat it either fully or partially. Like in Indonesian language, exotic examples in Indonesia and Motu languages, but also less exotic examples like reduplication in the perfect tense in ancient Greek, or even the way of forming the Italian superlative degree, you know, by replicating, by doubling the same adjective. This is not a kind of emphasis. This is some sort of grammatically encoded device, the repetition of an adjective, the reduplication of an adjective in order to form the superlative degree. So, in a sense, this also is related to a fairly well-known criticism of, addressed by Gary Marcus to multi-layer perceptions that relies on many nodes per variable representation, which are allegedly unable to replicate identity relationship unless the network sees that relationship instantiated in relation to each possible input and output node. So, what's the relationship between kind of positional models and this kind of discussion about variables and containers? Well, in competitive queuing here, for example, you have a kind of disjunctive representation of the context and of the item. So in the upper half of this slide, in this kind of gray band, you have a representation in terms of activation of two nodes, graded activation of two nodes. We have a representation of context through time, and you have the representation, the invariant representation of the very items in the bottom half, right? And you just reset your context in order to reproduce a particular sequence, reset your context to the stage it held at the time that particular string, in this case prop, was presented. By go through the steps of activation, you know, and through through this kind of time units, you can activate the various items in the proper order. The most important thing is that you have a kind of a disjunctive representation of context and items. So you rely on a kind of container view of variables that can be instantiated by filling them in through different symbols. That's the kind of reason positional models, which appear to be at this stage at least, I don't know, there are among you some experts or some people, some people interested in this kind of issues. At the time, this kind of positional models seem to receive, you know, seems to be the most credible and explicatory ones in relation to the phenomena we've been dealing earlier. But there is a kind of issue, which I already mentioned earlier, that concerns the relationship between long-term memory and recall. An issue that was raised initially by Badley in the late 60s and was called the bigram frequency effects, which has to do with the kind of chunking things that was also, you know, noted by Miller in the famous article in 1956. The fact that background knowledge matters when it comes to recall. The fact that some particular sequences have a kind of entrenched frequency, for example, in our lexicon or in our domain knowledge, whatever that may be, plays a role in easy of recall of certain sequences of items, right? So there is an interesting interaction here between long-term memory facts and the way they backfire in as well, or reflect onto our ability to recall sequences of strings. There is also a kind of slight paradox here because, well, the relevant background knowledge seems to involve transition probability among specific items. It seems to involve a kind of chaining mechanism which is deeply entrenched in our long-term depository of facts, which is something at odds with the kind of evidence that seems to dispute the fact that we have a chaining mechanism for reconstruing this kind of or list in recall experiments. But I think the most interesting point I would like to draw your attention to, this ends with the first half of my presentation for what concerns serial recall facts, because now I move to the kind of architecture I announced earlier, and the possible connections between this architecture and these facts. I mean, the central point is that it seems unrealistic to propose two radically different ways of accounting for serial order effects. One account that has to do with the short-term memory effects, according to which we have some transient associative activation patterns which account for single trial learning and recall, but are bound to decay in a short time because they are responsible for short-term effect, for short-term activations on the one hand, and the fact that we have to omit the interaction of this phenomena with sustained pattern of activation. Sustained pattern of activation which are deeply entrenched in our background knowledge, which apparently are due to repeated exposure to systematic regularities that we found in input series and in our background knowledge, generally speaking. And the technology that has been proposed to capture these facts, this long-term entrenchment, has to do with gradual adjustment of associative connections. So these are two different mechanisms that account to different facts that, however, interact in some prominent ways. We should strive to find a kind of overall machinery that take this kind of interaction into proper account. Right? Well, one of these attempts has been the connection in answer, which has recently been proposed by Botvinnik and Plaut, which, well, basically reflects the idea that sustained activation by recurrent connectivity proves to be able to develop item representations that appear to be independent from either preceding or ensuing items, which means that basically connectionist models are not chaining models, because representation of items in the list are independent of what goes before and after them, which is interesting because nonetheless, these kind of representations, which are conjunctive representation, where item and context are represented in a kind of conjunctive way. Do you remember the kind of Wickegren representations that I showed earlier? Nonetheless, in spite of this, these kind of sustained patterns of by recurrent connectivity capture a notional sequential structure through sensitivity to item transition probabilities. In other words, they manage to take into account interaction effects between long-term sustained activation and short-term recall. So this is a kind of fairly novel proposal. I think it dates back to 2006 or 2007. It has these interesting properties. Well, just to make a short summary of what we made so far, what we pointed out so far, pure chaining for most reasons, because they cannot take into account what we call structural confusability and other related phenomena, because there is empirical evidence to the contrary. Pure chaining models are not variable. Ordinal models, unfortunately, incur in the same range of problems, in spite of the fact that they are inspired to a kind of Italian cultural and anthropological model, are not sensitive to both position and domain-specific knowledge. Positional models, at the time being, seems to make use, seems to be in the best position to account for this phenomena, but they make use of disjunctive representation, as I showed to you, of context and items. They account for some sort of benchmark phenomena concerning confusability, but unfortunately they make no connection with long-term domain-specific regularities in serial structure. Activation connectionist models go some way towards achieving that objective, and they can also account for some benchmark phenomena which are related to errors in serial recall. But there are some interesting issues they do not manage to address. The fact that, for example, backpropagation, well, is claimed to be not biologically plausible. Probably some of you have different ideas about that, but I will not insist on this point. And then there is this issue of universally quantified variables that apparently cannot be represented by this kind of models, and they apparently play a crucial role in positional models. You remember the metaphor of placeholder and then items to be filled in these place models. Now, as a general comment on this, I think these two kind of quotes say a lot about what is still to be done in this particular field and what is of interest from our point of view as computational linguists or cognitive scientists. Empirical results in serial recall models seem to suggest that in addition to local position item association, an important role is played by higher order global information relating to the sequence as a whole. Such as global processes seem likely to involve chunking, may be analogous to Gestalt processes in perception in that they cannot be reduced to additive combinations of local features of a sequence. This seems to point to the issue of structure in language, or in serial recall, generally speaking, right? We need some sort of global constraints that cannot be thought to boil down to some sort of local connections, right? Well, in some sense, the kind of model I'm going to suggest, there is this missing here. Okay. So what I'm going to propose here as a kind of very short description of the way this type of neural network works. These are called self-organizing maps and can be conceptualized as a kind of grid, that kind of grid that you see on the right, usually a bidimensional one, grid of adaptive memory traces, which may be called, just for easier of recall, in a sense, receptors, right? So these receptors show a kind of dynamic behavior, which is an adaptive one. But at the same time, it is something I want to point out to your attention, a kind of short-term and the long-term dynamics. The short-term dynamics is that when they are exposed to a given stimulus, they activate. They get activated. And the degree of the activation is a function of the similarity between the content representation, which is held by the receptor, and the particular stimulus the receptor is exposed to. Yes?
You're probably about to say this, but what is what kind of object is the
stimulus?
Well, the stimulus, it looks like from your picture, is going to be a string of points.
Yeah.
But what is the content of the receptor?
Yes. I will talk about it in a minute, actually. I mean, it's a kind of vectorial representation which has the same dimensionality as the stimulus.
So it's also a single string?
Yes. It's basically a string or a vectorial, translation of it. Well, actually, the content, when the network is tabula rasa, is just white noise. It's kind of random activations of things. I mean, there is no wide-end content in this
Sure, but a receptor, for example, wouldn't be a grammar.
No. It would be just a string.
Something like a string or all the engrams that appear in a particular string.
Yes, correct.
That's or a subset of it.
Yes, absolutely. So the degree of activation between this internal memory content, which is associated to the receptor and the stimulus, is given by the degree of activation by the similarity, which is usually calculated as a cosine between two vector representation between the receptor and the particular stimulus. So take the most highly activated receptor is known as the best matching unit. When the network is exposed to a given stimulus, all receptors get activated in parallel, and the degree of activation is a function of the similarity to the stimulus, and the most highly activated stimulus is called the best matching unit. Then you have, this is a kind of short-term dynamic, right? Every unit or every node gets activated. Then we have a kind of long-term dynamic, which is adjustment of the weights in the internal representation of each receptor. All receptors adaptively make themselves, sorry for the mistake, for the misspell, adaptively make themselves more similar to the current stimulus as an inverse function of the physical distance from the BM view, the best matching unit, on the map. So you have a kind of bidimensional the grid. So the physical distance is the Euclidean distance between 2 points on a kind of bidimensional grid, right? So this is a kind of long-term dynamic. So we have here a nice kind of environment which makes these two aspects, the short-term dynamic and the long-term dynamic, interact in some interesting and trivial ways, especially because they are based on the same fundamental principles of activation and adaptation. So what is the expected behavior of this kind of family and unit networks? For example, you have local adaptation. At each iteration, the BM as some of its neighbors become more similar to the firing input. So you have a kind of specialization or sensitivization, if you wish, to a particular class of stimuli. Then entrenchment. Frequently occurring stimuli develop faithful memory traces, in the sense that these memory traces, for example, if the stimuli are some sort of very frequent strings of characters, or very strings where inflective forms like said, or got, or been, tend to have a deeply entrenched representation in some of the receptors of the map. So you have one particular receptor which is specialized for reacting or for being particularly sensitive to that type of stimulus, saying, hey, when I see said, I'm the only one who gets activated because I got specialized for recognizing that particular type of input. But also you have some interesting and non-trivial generalization effects, because due to a phenomenon of memory compression, for lack of room on the map, similar stimuli compete with one another for the same memory traces, basically. Due to the superposition of character memory traces, in the same area, we have some abstract traces will develop that are sensitive not to a specific item, but to a class of items. Well, the interesting fact about feeding these maps with inflective forms is this generalization of this class of items represents some morphologically natural class of words, class of items. So they got specialized like the XED corner that I put on the top of the map, specialized for recognizing, you know, all the words that and in a certain way. And then you have some sort of global topological organization, which is due to neighbor adaptation, so that similar memory traces cluster in topologically connected areas on the map, clustered together. Within any such area, traces show gradient similarity. So you have gradient similarity, generalization effects, entrenchment effects, which are due to the frequency of specific items, which are general properties which are nice, at least in my view, from the point of view of the representation of the way morphological information is organized, dynamically organized in a mental lexicon. So you could see these maps as a kind of metaphor, a kind of computational surrogate of the mental lexicon. So this is how a kind of 5-minute crash course on self-organizing maps and the potential consequences for, you know, language learning in the specific domain of word learning or morphological learning. Now, well, there are some formal bits that probably you might be interested in, but I will skip through them fairly quickly. So you have the so-called output space, which is this grid of 15 times 15 overall cells. And then here you have this kind of representation of a receptor unit, which contains some sort of vectorial representation of some vector representation of some kind. But you have obviously only, well, you can define network distance of an R² dimension between points into this bidimensional plane or bidimensional grid. And then you have this stimulus that define the input space, it gets a certain dimensionality. The interesting thing is that the receptor unit and the stimulus vectorial representation share the same, have the same dimensionality. Dimension, numbers well, this is the way we thought you could feed a particular self-organizing maps with a sequence of words. First, you split the sequence of words in sorts of trigrams, thanks to a particular, kind of trigram function. So stato, which is, past participles of the verb be in Italian, can be split in this kind of sequences. And then each trigram is first projected into a kind of representation, giving a kind of vector representation for each of the symbols in this kind of representation. Each of the characters making up a particular trigram is related to a particular vector representation. In case we are dealing with segments, this kind of multidimensional representation embody, some sort of acoustic or articulatory features of some kind. So once you get your vector, which is your recoding of your symbolic units, you activate, on the basis of this vector, you activate all the possible, in parallel, all the possible receptors in a map. And you have this distributed pattern of activation here, which is the result of this activation process. Well, in order to, but this only the activation state, which is triggered by one single trigram. In order to have an overall representation of the whole word, you have to overlap different patterns of activation. You want to integrate different patterns of activation, one for each of the trigrams making up the word in question. Okay, this is the activation function, which is basically the cosine and nonlinear function applied to the scalar product between the two vectors, the stimulus vector and the input space, the receptor vector. Sorry. And then eventually, as I anticipated, when you integrate this representation, this is the pattern of activation you get by feeding this particular word into this map. This is the way we deal with a kind of symbolic strings or kind of symbolic structures of list by turning them into some spatial or topological organization. So we are turning time series into some sort of bidimensional patterns of activation. So we are turning basically time into space. And this is the way, for example, the word's getting, the first trigram and then the second, and that the integration of the various patterns leads to this kind of pattern of activation over the two-dimensional grid of our self-organizing map. Yes. Yeah, sure.
One more.
Here or yeah. Sorry, this is a kind of.
What I'm wondering about is that I didn't see how the order in which those trigrams appeared
Is preserved. Is represented. Yeah. Yeah, that's the same question as yours. Yeah. Actually, it's not represented. I mean, due to this projection, the order is literally lost, although it can be recovered through concatenation of these trigrams. But from the formal point of view, you're right. You get the right impression.
So
Basically, by projecting, the time series into this kind of topological representation, if you have, repeated instantiation of the same trigram in the word, you get a double activation in the same topological area. Correct. Which may be a problem if you want to reconstruct the whole thing, but usually, well, you can show that is only rarely so.
Does it make a time-token distinction? So do you get the distinction between stato and statato?
Say again, the distinction between?
Stato and statato.
Stato and statato. Well, it could be the things slightly worse, but in fact, I don't think in this simple example you have to come up with some trickier example in order to have a truly ambiguous representation. Well, this is slightly different from the classical kind of Wicklefon's trick for a couple of reasons. But if you don't mind, I can turn back to this issue in question time because I'm a bit short of time. So, well, this is the kind of short term activation that I was talking about earlier. This is the kind of long-term learning step, which is called the long-term activation, which is the kind of adaptation step. So basically, the idea is fairly clear. There are some mathematical juggling here, but I hope to have managed to get across the basic idea. You want to make one particular unit, the winning best unit, more similar by incremental steps to the input stimulus, so that that particular unit gets specialized. And in order to do that, you have to use a simple incremental function by adding, by small increments, by altering by small increments the vector composition which is related to the best matching units and all the units which surround within a certain area of that particular matching units in such a way that it looks more similar to the input. It tends to react more actively and more highly when the same stimulus is seen again, is found again in the training data. Right. Now, the kind of novel architecture, this is the basic functioning. The basic functioning of self-organizing maps. This is where, our architecture adds some spin to this picture, in a sense. Well, here, we actually structuring this kind of maps in a kind of cascaded way, so that we project trigrams on the first map. We get this overall pattern of activation corresponding to the activation of the map when a particular inflected form is seen. And then we project the state of activation to a higher level map. So here we have the organization in terms of trigrams, or if you want to be more realistic from a linguistic point of view in terms of syllables, for example. You can think of trigrams, of course. This is a kind of practical shorthand that computational linguists often use, to make things slightly simpler. But you can think of them as syllables, which are projective, determine an overall pattern of activation at the first level, and then the overall integrated pattern of activation is projected at a further higher level. So we expect to find a kind of phonotatic organization at this level, with more frequently occurring syllables, getting a more entrenched representation in this first level map, and then if all these syllables make up coherent words and you project this integrated pattern into the higher map, what would you expect at this level would be a pattern of morphological organization of input stimuli. So that's the basic trick. So you have a sort of chunking mechanism there, and you have hierarchical levels of linguistic organization through this simple mechanism of cascaded input and cascaded feeding relationships. And this, this is basically what I already said. Input words are sampled at short time intervals and are input to a first level map. Due to the long-term learning dynamics, frequently occurring trigrams leave faithful memory traces. And at the same time, due to the short-term dynamics, the first level sum provides an integrated language-specific encoding of phonotatic sequences. Language-specific because, of course, in different languages you would find, or you would expect to find, different kind of syllables or different kind of patterns of entrenchment, a different overall topological organization of these phonotatic patterns. Actually, if you train, trivially, if you train these first-level maps with the phonotatic at two different languages, you get maps which are sensitive to different aspects of the phonotatic organization in the two languages. So the same sequence will not get, as a result of the activation, the same representation in two different languages for trivial reasons. So now, what do you get? Well, in this case, I emphasize a point that was raised by some of you at the level of the first level encoding. Time-coded signals are basically turned into topological representation. This kind of chains, this kind of landscape. The second level map will get the level of organization that we tend to consider a kind of second level or morphological organization where you find, well, probably you find some sort of organization patterns which are already found at the level of phonotactics, because you have something like ito, uto, ato, ano, ono, etc. But the most basic difference between trigrams in the first level maps and trigrams in the second level map is that these are kind of morphologically natural classes, because these are inflectional endings in the conjugation system of Italian. So these are morphologically relevant and morphologically natural classes of things. Yes?
Can you comment a little bit, maybe you will sooner, on the parameters that you, choosing the parameters of this model, such as the size of the grid and even the dimensionality? I can imagine, well, I mean, 2D produces nice pictures, and I could even think of a cute justification that the number of neighbors, 8, is something like the magic number 7, but I'm not, I'm wondering how much it really matters. It's obviously going to affect your distance function.
Well, your question actually connects with the issues of evaluation concerning the performance of the particular behavior, particular families of maps of this kind. Actually, I will provide some evaluation data in a bit, although in a kind of fleeting way because of time. What I would like to say is that at this stage of our work, we are mostly interested in the dynamics of this timing network. So we are trying to play with several different configurations, with several different parameters, to better understand the dynamic evolution, dynamic behavior of this kind of networks. So a short answer to your question is well, the dimensionality of the network depends on how much memory compression you want to achieve, and how fast you want the system to converge on the expected solution. And also depends on how many different types of words you want the particular map to be exposed to. So it depends on several issues. It depends. So I have no ideal answer or ideal configuration or ideal parameter configuration to suggest. I'm only saying that at the time being, I'm mostly interested in the kind of dynamic behavior that you can...
I mean, as in other words, in self-organizing maps, it usually is 2 dimensions because it produces nice dimensionality.
Oh, you mean the dimensionality of the grid? Why it's a bidimensional one instead of the 3-dimensional one? Well, usually the short answer to that is because it can be inspected more easily. It can be looked at, as you said. I mean, it provides a kind of more nice features. Although I think I'm really considering to add a further dimensionality to this kind of. For example, time, to respond to the kind of issues that time raises in connection to the ordering of these bits, probably time will be a further dimension to add to this kind of bidimensional grid, but this is a kind of speculative answer. I thought you were interested in how many, receptors or how many units you want to... Yeah, that's related by another question, right? Yes, please, Bob.
The 2-dimensional organization that we see now
Yeah.
of the conjugation classes, are you going to say some comment about it?
Yes, in a minute, yeah. This is actually a fake. This is something that I just drew for expository purposes, but there is another table which reflects a kind of current experiment. For example, this is a kind of organization that we get by exposing a particular map to forms of the infinitive in Italian and forms of the past participle. This is the kind of overall organization that we get, where you have some kind of default classes which are represented by the infinitive forms in are. Are is the first and more regular conjugation in Italian, which is also reflected by this huge pattern of activation with all the past participles ending in ato, while you have, kind of a wide variety of subregular past participles, like those ending in to, so, sto, etc. One of the things I particularly like about this map is the fact that it actually proved to be able to produce something like this kind of ending in etto, which is not attested in Italian. It's a kind of overgeneralization concerning a possible regular past participle of second conjugation verbs. We have only, well, to my knowledge, only one minor exception. There is a verb secreto, be considered an instantiation of this particular type of past participle, but actually it would have been impossible for the map to develop a single trace just devoted to the recognition of that particular past participle. So this is a kind of gradient effect due to the pressure of the ere pattern, which stands for the infinitive, the second conjugation verb, and the auto pattern, which is the pattern for the past participle, the regular past participle for second conjugation verb. We have a kind of blending effect there, which leads to this kind of incorrect overgeneralization, as a matter of fact. Here are some comparative results, and then I will go to some final comments, because I think, well, some comparative results concerning the overall organization of English and Italian conjugation systems at comparative levels of training. And we give also levels of global accuracy here for the two things. And this is, well, one of the results emerging from recent work that I've done with some colleagues, showing that basically we have, we train with these particular forms, which is the base form, the past tense and past participle forms, the present, the S present in English, and the progressive form in English, and you train with a compatible set of forms, of Italian forms, the same map, basically, with the same dimensionality and same kind of biases. You get, at the same level of training, a more coherent organization of Italian data compared with the data of English. Well, this is an interesting piece of evidence because
Percentages reflect, I'm sorry.
accuracy, the way actually you can interpret this as a kind of classifier, right? So the response of the map tells you whether one particular string, one particular word form has been classified correctly or not, whether it's been classified as a past participle and whether it is a past participle. So the accuracy is the figures concerning how many times one particular string was classified in an appropriate way.
And these are for novel forms that weren't in the training data?
Yes,
Okay.
yes.
And the training data was unlabeled, is that right?
Yes. Well, it was labeled, though the label doesn't interact with the training. It was labeled because, in a sense, we want this particular map. This is a kind of technical detail we can discuss later because it's slightly counterintuitive. Well, if you label these particular nodes, I mean, without making these labels interact with the training process, you can then easily evaluate the accuracy of the map.
It's unsupervised training.
Yeah, it's anyway unsupervised.
Right?
Although you have to know what a particular, yes.
Yeah.
Okay, that's the short answer. And this is a piece of evidence which supports some empirical evidence about the way children actually converge onto the development of present indicative paradigms in English and Italian. Actually, there is an advantage in learning Italian, which is a more complex paradigm, than learning English, which presents a kind of, very syncretic kind of paradigm for the present indicative, where most forms, are presented in base form, with the only exception of the third singular person, which ends with an S. Well, a kind of rule-based, intuitive, and if you want, naive approach to the problem would be that since a child has to learn only one inflection ending in English, while it has to learn 6 different inflection endings in the present indicative of Italian, the English child should converge on the mastering of the present indicative paradigm earlier than the Italian child. Actually, this pattern, the empirical data do not support this intuition. Actually, the Italian children converge into the right sort of present indicative paradigm earlier than the English children. And the functioning, and this is basically based on the principle of contrast, the fact that you have to master a number of forms that are contrasted systematically in the Italian paradigm, while they are not so in the English paradigm, because you have base forms which, differ from one another in kind of unpredictable ways. So while there are attractors, systematic attractors in the Italian paradigm, there are no such attractors in the English paradigm. And these make things slightly more complicated, and this gives us a strong intuition that probably what matters when it comes to, the learning of an inflectional system or a morphological system is the overall mastering of its paradigmatic structure, and not just, a correspondence between, a base and an inflective form, which is the usual derivational paradigm. Both, I must say, this is a topic I will discuss and harp on in the next talk in 2 days, both from the point of view of rule-based models, but also from the point of view of connectionist models. Connectionist models, the traditional backpropagation, perceptrons, actually endorse this implication that producing an inflective form is like deriving an inflective form from a base. Probably from this perspective, things look slightly more complicated, but even more realistic, maybe. Right. Well, you can extract also the patterns. We made experiments also with Arabic. This is just to show the advantages of this kind of projection from time onto space, because you are not constrained by alignment issues, time alignment issues, because, obviously in non-concatenative templatic morphologies of this kind, the kind of alignment that you want to enforce on the data, the kind of correspondence that you want to establish between similarly inflective forms are different from the kind of patterning or the kind of alignment that you would like to enforce with concatenative morphologies. In concatenative morphology, you have to think of the head and the tail of a given string, while in non-concatenative morphology, you have to think about, the interdigitation of consonantal skeletons and vocalic patterns. By the way, probably the kind of evidence I mentioned earlier about the propensity, the bias towards primacy or recency effects will be a factor that would make us understand a typological observation, the fact that we have more concatenative languages attested all over the world than non-concatenative languages. Probably concatenative languages respond better to this kind of primacy and recency effects, because you have to look and remember the first part of the word and the end of it, and you can get away with it, while with this kind of patterning things are just slightly more complicated. So there are not kind of iconic or semiotic factors involved in this, as claimed by, for example, natural morphology, but only, microdynamics concerning the interaction between short-term and long-term memory facts. Well, here I exemplify the different type of alignment phenomena that you can have with different languages. Head and tail. In Italian, you should look at the end. In German, you should look, for some phenomena, of course, not for all of them. You should look at the end of at the beginning of the end. And in the case of Arabic, you should look to this kind of vowel with patterns. Well, this is the end of the story. Axioms, what's the relation between asynchronous self-organizing maps and the problem of series structure? Well, as I emphasized, as I pointed out, they tend to de-emphasize the role of local position item associations and the importance of global constraints by mapping time series onto spatial patterns in such a way that, as was already pointed out earlier, representations are largely independent of time alignment. They seem to lay emphasis on global similarity-based effects of topological organization of the kind of paradigmatic patternings that we've been talking about so far, which are enforced, and this is an important point, through local processing learning steps. The learning steps that get to this kind of global organization were local, were incremental and local. So we are not assuming that the child is somewhat engaged in a sort of global optimization problem for example, as in other learning algorithms like the minimum description length algorithm proposed for unsupervised discovery of morphological structure by John Goldsmith. But that is a kind of global optimization problem. You here manage to have a kind of global coherent topological organization by small incremental and local similarity effects involving also, only the best matching unit at one particular stimulus. Is a kind of pairwise relationship, so a local form of analogy. Account for grouping effects, which are conducive to consistent sampling of short-time scales. Well, grouping, in a sense, is a way of sampling the input stream coming to us. This is a possible interpretation. Sampling in a way that is maximally consistent with the particular nature of the input stream. Right? If we put a pause or we give a kind of rhythm to the string instead of providing the same string as evenly spaced items, we are giving hints of possible segmentation which are consistent from the point of view of the structure of the signal of the time series we are trying to process. Well, seems to be able to enforce hierarchical chunking through cascaded projections. Moreover, account for emergent patterns containing universally quantified variables like XED. I didn't talk much about that, but this is kind of a side issue, of a side comments that I would like to make. Well, obviously, there are some further developments that we would like to try. For example, so far, trigrams. Why trigrams, for example? The length of the sampling windows are stipulated by the model. Maybe it could be made more dynamic and made sensitive to graded frequency effects through mechanisms of recurrent feedback relations. There are some recurrent self-organizing maps which seem to be promising in this respect. They have been recently proposed by Verklen. Short-term activation should be single trial, not crucially dependent on past targets during training. This is a kind of mechanism that seems not totally convincing to me. The fact that we are making, short-term recall dependent and crucially contingent on the presence of already entrenched memory traces in our model. This is not totally convinced, so we should be able to give a better account because, the kind of empirical evidence that I illustrated point into this direction. Domain knowledge should be helpful in augmenting recall span, but should not be taken as a kind of precondition to recall. So short-term and long-term memory processes call for a better integration and should not be taken as just one step. And then reduplication effects, which was another issue which I touched upon, in the first half of my talk. Reduplication effects are hardly captured by our system. So still this fact that you have, you cannot replicate a kind of identity relation between groups of strings is not an issue that we tackled and we solved yet, by no means. This is something I think we should work on intensively. And then, basically, this is what I want to say. Thank you for your attention, and that's it. Thank you.
Any questions?
Yes.
Maybe you can help me understand how you think of the function of this system that you're talking about.
Well,
So, it's not the case that this second level map provides something like a lexical, an encoding of a lexicon in which we can look to it to store lexical items. Possibly the first level map could do that. I don't know, but typically we imagine networks either providing lexical access or doing an inflection mapping or something. So what function do you see this thing actually
Well, yeah, that's right. The intuition is absolutely right. The second level map cannot be taken as a full kind of morphological lexicon, because if you try to find what is stored in each receptor in the memory traces traces that are associated with each receptor, you would not find full words. So that's not a possible kind of lexicon. It's a kind of hash coding to the lexicon. It's a kind of way of classifying your items of the lexicon and organize them kind of morphologically natural classes, in the sense that you would expect, to find all, some pointers to all the morphologically related words ending, in a certain way, in a certain area of this lexical map. And then another possible potential function would be that of a classifier. In fact, I mean, by projecting one particular stimulus on to one particular area of the map, you will be able to predict, even though that particular string was never seen, or it was never part of the training of the. You will be able to classify this kind of string correctly as being, I don't know, past tense or aim form or whatever. So you may think of it as a kind of hash coding of a lexicon that must be there somewhere. And this provides a kind of morphologically grounded interface to get access to this information. That's as I see it. Well, originally these kind of maps were intended as a kind of classifiers, basically some kind of classifiers. The interesting thing is that they managed to do that by developing interesting morphological generalizations by small incremental steps. So they managed to get to this kind of a global coherent organization of the morphological step in an unsupervised way. We are not telling the map where to look for this kind of generalizations. The map can be exposed to, templatic patterns or whatever. And this is part of the learning process of the map, focusing on the right sort of, bits or units in the string which are morphologically relevant. While, this problem is not really tackled by traditional backpropagation models, where you try to enforce a kind of alignment between the input and output representations for some morphological generalizations to develop. I'm thinking of particular templatic representation that were used, for example, by Plunkett, and Juola in recent work, where they try to align, the plural of some nouns through some sort of templatic structure that has a kind of phonological flavor, but in fact does not meet phonological requirements. Why the interesting thing here is that it is unsupervised in two ways. Is unsupervised in the sense that we are not tagging a particular string of words. We are just providing the form of that word, but it's not supervised in the sense we are not telling the system where the regularities should be looked for. And this is interesting. This is the result, the emergent result of a process of global organization of the morphological space. And that means that if you reason in terms of paradigmatic global ways of organizing our morphological input, we eventually get to a kind of morphologically natural organization, even without supervision. This is not intended to mean that, the input of the child is only forms. Well, it's much more than that. But this is intended to show that even on that very basic level, the child should be able to bootstrap a certain amount of morphological knowledge. This seems to be, coherent with what we know as a linguist about, the way a kind of morphological lexicon should be organized. But you're right in the sense that these second-level maps I was showing are not, in a strict sense, kind of long-term repositories of lexical knowledge, because they are kind of generalization interfaces or generalization tools. Yes. Yes. I see many hands, so you first. Sorry. Okay. I mean.
Okay.
Yeah. 1, 2, 3. Okay.
So you spent a long time introducing serial order, which I really appreciate, and then you went on to talk about axons, but I'm having a hard time.
Yeah, in seeing the relationship.
So I'm just wondering how they're related.
Right. One issue I try to emphasize was this kind of dynamic. Well, the question was, there are two lines of thoughts I try to pursue. The one is that, well, this kind of serial recall literature is extremely interesting. I think we should look very hard into that because it provides a kind of insightful, remarks concerning the microdynamics of the interaction between short-term and long-term memory issues, right? This is incredibly interesting, and it should help us to focus on some basic mechanisms of representation of order and time, in cognition. So that was the first thing. The second thing is that, well, there are some connectionist architectures, which, like the one recently proposed by Botwinick and Plout, which claim they can address some problems of this interaction in certain ways. Well, the connection is that by showing to you, I did not do that, I did not spend enough time into that, but I was trying to show that even a better interaction between short-term activation and long-term activation is embodied in these kind of maps, because you have one mechanism of activation which is based on local similarity between the memory trace and the grid and the input stimulus coming, and the same mechanism of similarity activation accounts for the entrenchment of these traces, for the entrenchment of the input stimuli into the map. So basically we have the same kind of mechanism. So we have a potential. I did not show that they potentially can solve some of the problems concerning the interaction between short-term and long-term memory issues. And another thing, another possible parallelism was with the issue of grouping. So what's the role of grouping? Why grouping should affect positively our ability to recall certain structures? Well, if you imagine this kind of a hierarchical, organization of our input stream, well, probably the kind of rhythm that we introduce to influence grouping of some kinds may provide ends for sampling your input string in a way that is coherent with the structural properties which are hidden in your input string. So there is another connection. I admit the connection is still a kind of, impressionistic. We did not explore that. But concerning the interaction between short-term and long-term memory issue, the need for global organization, for global structure to be imposed. Well, this is one of the points you raised in our informal discussion, the need of organization, of hierarchical structure. They should be hidden somewhere there. And I think this family of networks can account, at least to an extent, for those phenomena. It's still tentative, I agree.
But so these networks don't do serial monitoring.
Well, you can try them for these kind of things. You can activate them, and you can see how much of this kind of short-term activation is preserved after a certain decay time elapsed. Things like that. These are ways of... Actually, we have some preliminary experiments, but still too preliminary to talk about that. Sorry. Yes?
My question is about the limitations placed by using those trigram representations on what the axon can learn. So, for example, I was impressed that it could learn these things like the Arabic, where you had an A, and then a space, and then an A. But I was wondering if it could learn that type of thing where the space was... It doesn't seem like it could learn that type of thing where the space was more than one consonant, for example.
Right, yeah. Yes, that's true. I mean, there are some limitations which are connected with the type, obviously connected with the type of representations that we choose. And this is the point I kind of touched upon fleetingly in the last few slides. I don't remember which one, when I saw that obviously the choice of trigram is a kind of stipulative and arbitrary choice. Why should we choose a trigram? As you said, I mean, even some morphemes can span more than one trigram. But in fact, you can account for that because you get an integrated picture of the various trigrams, and you project to a further level. So through integration of these trigrams, if you're lucky, you're likely to get some, morphological phenomena which span over more than one trigram.
You cited the German case where you have
Yeah.
the A and then the T at the end of the word. Does it capture that?
We didn't try, to be honest with you, we didn't try that, so I cannot be assertive on that. But yes, surely there could be problems, with long distance kind of, interfixation like that. Yes.
Because my question was related to the one previous question, just kind of how you segment the different trigrams if you're doing a sequence. It sounds like that is an ongoing research effort.
Well, yes. Well, very simply, actually, by sliding the window one character at a time. So you have.
But for a continuous input, how would you do that?
Well, I didn't see a particular problem. Well, obviously, yeah. Now I can see your problem. I mean, obviously, there is an issue of word segmentation there, which I kind of, skipped. I'm assuming that in order to integrate the right sort of trigrams to get, a representation of a word, I'm assuming that you have some kind of segmentation of your input stream into words. Yes, you're right. This is the kind of preliminary assumption. There was kind of covert assumption. So I assume that you have ways of segmenting your input stream into words. So you can consistently project your first level representation into a second level representation at the time a particular word finishes, ends. Yeah. You have to require that kind of, you have to make that kind of assumption. You're right.
And you haven't looked into that?
Yes.
I have two questions about the hierarchy, right? The different mappings from one level to the next. They might be related. In my mind, they seem there a little bit. The first is, you were talking about that training is, in the axons, is not supervised. But you are, as I understand it, the way I'm thinking about it, you are deciding at what points one level projects into the next, and what kinds of information is there. So
that's related to the question he was raising. Yeah.
Okay, so you are then, in a sense, you are deciding at some level what degree of structure. I guess what I'm thinking of is because what I'm ultimately thinking about is one effect of serial order that's very interesting in spoken production, as I'm sure you know, is just that the structure of the syllable will govern speech errors, so onsets will slip with onsets, but syllables don't slip with syllables for the most part. And so what I was curious about was whether if something if there's a stage in the hierarchy that exists in the network, let's say the syllable. Now there might be other ways to get onsets and things like that in your network. But if there's a stage if there's a stage in the hierarchy, do the errors, if there's some way of generating errors, or does the function of the network have to reflect it at all in all ways? So for example, if you were to have a syllables level in the structure of the hierarchy in order to get onsets and codas, would that also necessarily predict that syllables could slip with syllables in an error? I realize that you haven't implemented errors and so on.
No. Well, actually, what I was suggesting about the possible partitioning of words into syllables was a kind of tentative suggestion. I mean, we have not yet implemented that. This is something we would like to pursue, a line of work we would like to pursue. I mean, and that's one of the reasons why I'm here. I mean, this is a line of work that we would like to pursue in collaboration with some of the people here at the Department of Computer Sciences. So I cannot be assertive, or I cannot make predictions about that, but it certainly will be related to the kind of issues you're raising. I mean, this kind of, mismatching or this kind of errors you're talking about will probably be relevant to this kind of representation. Yes, but I cannot make more comments, on that, because this is really work that we intend to carry on,
Okay, we should stop here. Well, thank you.
Okay, thank you. Thank you for your attention.